Hello, hello again, everybody. I'm John Allway. Welcome to the third and final part of the Decoder Transformer tutorial, where we go through and discuss the major components in the pipeline. This is part 3, so if you haven't listened to parts 1 and 2, then I highly recommend that you do, since part 3 depends on the prior 2 parts. Okay, the next component in the transformer block is the feed-forward network, also known as the multi-layer perceptron. Feed-forward networks are the heart of deep learning neural networks, not just large language models like decoder transformers. Every deep learning model ultimately relies on feed-forward computation, whether a visual system, an audio system, or an LLM like this. They are able to learn complex relationships. And there's actually a theorem called the universal approximation theorem that applies to feed-forward networks. And what it says is, this is technical, they can approximate any continuous function on a closed boundary interval to any desired degree of accuracy, provided that they have enough neurons. With enough neurons, they can fit pretty much any continuous function. So it's a very powerful element in the in a network. Feed forwards are required for deep learning. They are the workhorses of deep learning models. Okay, the self-attention here system mechanism is unique to the decoder model, whereas the feed-forward network is common across all models. So that's an interesting difference there between the two. Okay. Okay. Now the next one is the feed-forward net. Some details on the feed-forward network with respect to the decoder transformer. Okay, so as was said, the self-attention mechanism is specific to decoder transformers, encoder-decoder transformers, and the feed-forward network is common across all deep learning models. In the decoder transformer, the feed-forward is a fully connected and nonlinear. This nonlinearity is what allows the network to learn complex relationships. And the FFN, feed-forward network, has 2 layers in this model, 2 layers, and it includes activation functions between the first and second layer. The activation functions, it can be commonly a Gaussian error, linear, Gaussian error linear unit, or rectified linear unit. The rectified linear unit and the Gaussian error linear unit and others are activation functions that might be used. I think GALU is used, I believe, in GPT-3. And these are what give the networks nonlinearity. This is what allows them to make complex functions, to model complex functions. Without them, the LLM, the feed-forward network, would not work. You need that the ability to model complex functions. Okay. Okay, each embedded vector gets its own FFN, feed-forward network, for parallel operations. In other words, when out of the attention block, each token in the and the embedded vector sequence is given its own feed-forward network to go through, usually on a GPU or set of GPUs. So it's all done in parallel. All the processing is done in parallel and very fast. This is the parallel architecture I referred to earlier. This is a massively parallel system that this thing can use, a massively parallel system, so it can be very fast at churning out data. I came up with an analogy for for the relationship between the attention mechanism and feed-forward network. The attention mechanism can be viewed as like eyes, and the feed-forward network you might view as a brain that the eyes are plugged into. So this gives this is the attention mechanism. This presents the data in the proper format, and this processes the data right here. This is sort of the relationship you might view it as between the attention mechanism and feed-forward network. It's what learns the feed-forward network is a brain that learns the relationships that the attention mechanism feeds into it. Okay, now I'd like to give a word. All right, next I'd like to give a word about transformer block stacking, or talk about transformer block stacking. This has similarities to the way humans learn, where we start with lower level concepts such as arithmetic and move to higher level concepts such as algebra and calculus. There's a buildup of knowledge, in hierarchical buildup of knowledge. So look at you can see these transformer blocks here as has been mentioned earlier. There's one after the other. There's several transformer blocks, usually in a row, in series, one after the other. One feeds into the other. And ChatGPT-3 has 96 of these blocks, one after the other, feeds one into the other. And these build up knowledge is what they do. Each TB adds a layer of understanding built on the previous. Each transformer block TB adds a layer of understanding built on the previous transformer block layer. So the first block learns basic level patterns. The next transformer block learns patterns of those patterns. And the next learns patterns of the prior block's patterns, etc. In so doing, knowledge is built up in a hierarchy, stacking block on block. By experiments, it's been observed that lower level layers recognize surface level patterns, such as what words are next to each other. Middle layers capture medium range patterns, for example, subject-verb agreement and phrase structure. Higher level layers capture abstract global or conceptual patterns, for example, the topic of a sentence, semantic meaning, and reasoning signals. So there is hierarchy of learning in these decoder transformers. It builds hierarchical knowledge layer by layer, and this has been shown in experiments to be true. Okay, now for the next thing, the final linear layer, this block right here. So this layer calculates the logits, by which I mean the raw, unnormalized scores to determine the next word. Final here means that this is where we get the max value output token that we've been seeking to predict. But as we'll see, it's probably not going to be the final choice, as we'll see in a little bit later. So coming out of the final transformer block out of here, the TBN, is a set of predicted words. Remember, every token/vector that came out of the attention blocks is sent through its own copy of a feed-forward network. The only one we are interested in, however, is the last word, since that is the next word to append to the input sentence. And this is true during inference. During training, all words coming out of the FFNs are the last block used. So this random selection is not in during training. It's only during inference mode it's used. The dictionary of embedded vectors, which we looked at earlier, dictionary right here, is used here. The dot product of every word in the embedded matrix, aka dictionary, is taken with every word in the dictionary. Remember, this is a set of all the tokens or all vectors in the dictionary. Say 50,000 for a GPT-3. They're in terms of a high-dimensional vector. Well, the predicted word is going to be a high-dimensional vector, and we're going to take the dot product of every word in the dictionary with that vector, and that will give you a scalar value, which is a score. So when you take the dot product of two vectors, you get a scalar, and that's a raw score. Now, the highest score is the one that would be matched if we wanted to take the one that was the best prediction. Okay, that's what this does. The logits, this creates a set of scores, and those scores are created by taking the dot product of the final word with every word in the dictionary of vectors, and the highest. And these are all raw scores. Every dot product in the dictionary is a set of raw scores. Okay, here is how logits are calculated. Remember, logits are raw, unnormalized scores. This is a straightforward calculation, and hopefully you get an intuitive sense of how it works. To calculate the logits, we take the last predicted embedding vector, elast, and that's the last out of the last transformer block. We get the last word predicted. We take that last word and we dot it with every single word in the dictionary, as I mentioned. And that gets you the set of all the logits, right? And it would look like this right here, something like this. The vector, and it'll be like 50, if the dictionary had 50,000 words, it'd be 50,000 score values there. Where W out is the dictionary of embedded tokens, elast is the last vector from the final transformer block. It's the last vector, last predicted token or predicted vector. You dot product and you get these kind of like scores like this in the end. And the one with the highest score is the best prediction. Okay, now about randomizing word selection. From the raw score that we got in the logits table, we can select the highest score, as I mentioned, but oftentimes we don't want the highest score. To be less predictable, we often want a score that is close to the highest. This is why inference models often randomize word selection. So choosing a word with the highest logic score would mean the model always selects the same output for the same input. So it's very predictable. To reduce predictability, logic selection is often randomized. Okay? Randomization is done in inference mode, not in training mode. It would not be useful in training at all. The output can be as random as desired, which can result in the decoder transformer producing some wild and sometimes very creative output, albeit also some very wrong output. Okay, so yeah, that's okay. Okay, there is a hyperparameter, which is a parameter you set at the kind of a global parameter for the model that can be used to adjust the level of randomness of the model. This is like a knob on the front end that can be adjusted. To randomize the logits, or to apply randomization, the logits are normalized using softmax on the logits we just calculated. So here you see softmax function is applied to the logits. Now remember what softmax does. It takes a set of numbers and makes it so that the set of numbers adds up to 1. And it also makes sure that it normalizes them by setting them up so that they all add up to 1. And so that each value is in the range of 0 to 1. So a value can only be in the range of 0 to 1. Softmax does that to the logit. So those raw scores become normalized, and I'll put it in this thing called probs. And the temperature, hyperparameter temperature, is added as what? When added in there, is like taking the is actually a value between well, one it has no effect at 1. It can flatten or sharpen the distribution of softmax values. So if t is less than 1, they become sharper and more confident. They stand out more. If t is greater than 1, they become flatter, more random. Normal softmax of 1, no scaling, it's just the same as without t. So you normalize the values, then you can apply t. You apply t before normalizing the values of the logits. So yeah, so t adjusts the sharpness or flatness of the probability distribution. And once we have the probability distribution, then there are 3 algorithms we can apply. Now, one of the algorithms, these are 3, okay? So the temperature we used sets us up for randomized selection of the word predicted, as does the normalizing with softmax. 3 common selection algorithms applied to the probability distribution vector we created. These are 3 common algorithms. One is argmax. We just take the high score, and that would mean there's no predictability at all. I mean it's 100% predictable when we leave it at just take the maximum score every time. It's always going to be the same result every time. However, if we take sampling, where it says random, which randomly selects a token with weighting toward the most probable, and here temperature has a big effect on this method, then we're going to more than likely take the ones with the highest score, but we could randomly take even the ones with very low scores here, which are more likely to get the higher score ones. Another one is called the top K, top P, and this restricts the set of top values range, and then randomly only selects the value from that range. And temp affects this one as well, because it affects what's in that range. So yeah, that's yeah. So. Okay, so once you have a word, you find now you finally predicted a word. You have, this is the word I want. Then you can take the ID of that word, put it in the embedded dictionary, and get the vector for it. And append it to the input sequence, embedded input sequence, and send it and feed that the input sequence plus the appended new word into the input of the decoder transformer, and repeat the whole sequence again. So it's going to go around again and predict another word, and then another word, like we said in the beginning. So and that will be the end of the pipeline, the end of the process. Remember, this is an autoregressive model. It predicts an output word from a sequence of input words. Yeah, that's the end of the pipeline. That's what it does. That's the whole deal right there. So now that we're done with that, I'd like to then go to a little bit on 2 more slides and that'll be it. Okay, I'll talk a little bit about meaning. Why is the decoder transformer able to convey real meaning when it responds to a query? Where does the meaning come from? I mean, how the heck could it know what it's doing? Okay, the decoder transformer is a statistical model. Okay, during training, the decoder transformer determines the frequency with which relationships or patterns are found, and from this builds up a statistical model. Okay. The building blocks of the decoder transformer are the tokens, okay, the word vectors, which represent words from text. The tokens are defined as multi-dimensional numerical vectors, i.e. embedded values. A decoder transformer learns entirely from data. Upon training, it determines the existing relationships between those tokens according to the frequency with which such relationships exist in the data. And we're talking about billions of documents go through these bigger models like GPT-3, and it figures out all the frequency with which these patterns exist, these relationships exist, and that's how it's coming up with probably a statistical model. And so the DT just contains statistical relationships among the words, okay? It has no awareness or understanding of the meaning of words. Like, it doesn't tie them down to reality. It doesn't know. It just goes strictly on how often a word is in a certain context. Like the word elephant, it doesn't conceptually know an elephant. It hasn't seen an elephant. Not aware of an elephant. So all of that kind of meaning comes from humans who wrote the words. And so you have to hope that the humans who wrote objectively true things, or the decoder transformer would relate nonsense. If you put in nonsense words, it would output nonsense to you as a result. Okay, now to the final slide. I wanted to mention that the decoder transformer has fixed values. Once trained, it's a fixed set of weights and biases. Okay? So this is the final slide of our 3-part lecture. Okay, so the decoder transformer always gives the same output for the same input unless you randomize selection. For a set A of input tokens, you always get a set B of output tokens, or an output token actually. You always get, for any particular pattern, you always get the same output pattern every time. It's very straightforward that way. And it's only randomization that changes things up. And that's outside the model, really. And I thought this analogy might work. It's like decoder transformer is like a light circuit with input switches that turn on a network of lights. The same input switch states always turn on the same lights. The only thing with the decoder transformer, you get billions, billions, trillion even weights and complicated relationships. So it's a super complicated light switch panel. Beyond, it's just crazy, crazy complex. But that's sort of what it's doing, though, nonetheless. The training is the interesting part, really. When you think about the training, how it sets everything up to know what it knows is the interesting part. But once trained, it's sort of like this. And the decoder transformer is powerful because it retains billions of weights and biases that are trained to accurately represent billions of existing relationships between words. So it's it's fascinating. So anyway, so that's a little bit on that, okay? And that's my talk on the decoder transformer in inference mode. I hope it was informative for you. Okay, I'll sign off, and good day to everybody.